Okay, so let's go ahead and get started. So I hope everybody had a good weekend. So we're coming back to talk about the electric potential and the electric potential energy today. So you'll remember I drew a chart last time that kind of arranged all of these equations. So I'm going to show you that again, and then we're going to talk about where it is that we're going to go for today. So we knew that starting out, if we had two charges and we wanted to find the force between them, we used Coulomb's law. And that was our force equation. So this says that the force is going to be equal to 1 over, well, we don't write it in that form, we write it in terms of K. So we have K, Q1, Q2 over R squared. This was some vector quantity. Then we talked about how we could write the electric field. So the electric field, we denote with an E vector. From a point charge is just going to be KQ divided by R squared, okay? And again, these are both vector equations. I'm just writing this as the magnitude of the vector, okay? Then we began to talk about the electric potential energy, and so if you think about two charges, the force they have between them, they're going to repel each other, but if you hold them there, you can treat that like the potential energy of a spring, right? You compress a spring and you hold it there. It has the ability to cause motion. So if I have two point charges with positive charge and I bring them close together and I hold them there, they have that same potential to be able to create some motion. And so the way that we describe that is to say that U is going to be equal to K, Q1, Q2 over R. And this is the potential energy between 1 and 2. And last time we talked about how we could find what the, we could find some velocity given if we said that we had some particle here, some plus Q, some plus Q, and these are separated by some distance D. And then we let it go and then see how fast this one's moving. Say this one remains fixed the whole time. We could determine how fast this charge on the right is going to move if this is some larger distance. In this case, we could say maybe it's some 2D. Okay, so that's what we talked about last time. We're going to continue with some of those calculations, but what we're really after is this bottom right corner. And if this is the potential energy, this is what's called the electric potential. And for a point charge, this takes the form V is going to be equal to KQ divided by R, okay? So when you think about it, it's kind of a strange abstract thing, and even when we're moving from our force to our electric field, it's some level of abstraction that we can say, okay, well, force is tangible. I can take these two particles and they experience a force. I know what that means in terms of acceleration. But then we're kind of imagining what happens if we say that, well, I don't really care about the second charge, but I can talk about some field lines that are produced by a single charge, and then I can say, well, if there was another charge there to experience the force, I know how that's going to behave. The potential energy to the electric potential is kind of a similar idea. So we could say, in the case of the potential energy, that I have two particles and I put them close together, and it has the potential to be able to move the object. And then we kind of take one of the charges away and we say, well, we don't even really need a charge there if we think about this in terms of ultimately this is going to be analogous to topographic maps. What does a mountain do? You don't need to know, for instance, if I have a mountain, I don't need to put something on the mountain to know how it's going to move. It's just going to roll down the mountain, okay? But we'll see more of that as we go through today. So to begin with, I have this problem where we're just trying to calculate what the potential energy of this system is. And so we have these four charges on the sides of this rectangle. And what we'd like to do is to calculate what the potential energy of the entire system is. Now, something to bear in mind here, you'll notice that there's some symmetry here. You can use that in order to do this calculation. And the other thing that you want want to do is you want to make sure that you don't double count. So if I say that I want to find the total potential energy of the entire system, that means what is the potential energy between every point. But you wouldn't want to count the potential energy between point 1 and point 2 and then count the potential energy from point 2 to point 1. We already took care of that by doing it the first time. Okay, so go ahead and spend a couple of minutes working on this one, and we'll go ahead and talk about it. Okay, so let's go ahead and talk about this one, and then we'll move on to the next one. So in order to find the potential energy of this entire system, what we need to do is to find the sum of the potential energies between all of the charges. And so in order to do that, what we really want to do is to find the potential energy between 1 and 2, and add that to the potential energy between 3 and 4. Add this to the potential energy between 1 and 3, and 2 and 4. And then also add in the potential energy between 1 and 4 and 2 and 3. But we notice something kind of interesting here because of the fact that this is a rectangle. These two are the same. So really I just need to double the potential energy from 1, 2. We see the same thing here and here. So we can factor out that 2. We can add plus U1, 3 plus U1, 4. So let's go ahead and explicitly calculate what U1, 2, U1, 3, and U1, 4 is. And really the only difference between these, if I start with this equation here, is the distance, right? Because the charges, they're all the same magnitude charge, right? Q1, Q2, Q3, and Q4 are all the same. And the constant K is the same. And to remind you, I should have written this down to start with, but to remind you, K is equal to 9 times 10 to the 9 Newton per Coulomb squared, okay? So if we plug the appropriate things in here, what we're going to see is this is going to be 2 times K Q1 Q2 over, let's call this R12, plus K Q1 Q3 divided by R13, plus this is K Q1 Q4 divided by R14. And there's a reason why I'm doing it like this instead of writing each one of these, this equals this, this equals this, this equals this. And that's because, like I said, there are common factors here. And so the advantage to doing that is I can factor out the common factors. I can factor out K, I can factor out the Q. All these Q's are the same. So this is going to be 2KQ squared times 1 over R12 plus 1 over R13 plus 1 over R14. And now that you have it in this form, it's one line with your calculator. Plug in for each value here. So this is 9 times 10 to 9 newtons per Coulomb squared times 1.6. Was it 1.6 or was it just 1? 1 times 10 to the minus 6 coulombs squared plus 1 over 0.03 meters plus 1 over 0.04 meters plus 1 over 0.05 meters. Okay? Sorry, this isn't a plus sign. This is multiplied by. Okay? And when you do that, you end up finding this has a value of 1.4 joules. Okay? Any questions about that? So it's not a very difficult problem, but I think the one takeaway that you can have from this is that you can certainly save yourself a little bit of time if you do this symbolically, and then you rearrange it before you plug it into your calculator, because you really only need to plug one thing in your calculator if you're clever about the way that you do it. Okay? All right, so let's move on to the next one. So for this one, this is a question about the electric potential now. And so remember when I was talking about the electric potential, going from the force to the electric field and going from the electric potential energy to the electric potential is kind of similar. You kind of remove a charge. So in this question, what we'd like to do is we would like to figure out an expression for the electric potential distance d from the positive charge q shown below, and how would this expression change if the charge was negative. Additionally, what I'd like to do is to start thinking about electric potential, equipotential contours. And so I want you to draw draw on your picture here lines where the electric potential has the same value. Okay, so go ahead and take a little bit of time to do that, and then we'll go ahead and talk about it. All right, so let's go ahead and talk about this one. This one's kind of, it's deceptively easy in a sense, right? Because there's not a lot to it, but the meaning of it is important. And this is really building into the conceptual understanding that we're looking for when it comes to the electric potential. And so what I tell you here is that I have some point charge plus q, let's say, and some distance d along the x-axis. And I want to find what the value of the electric potential is here. Okay? So in order to find the value of the electric potential, I can just apply the equation that I have here, that the electric potential as a function of r for some distance r away from the charge is going to be equal to v is equal to k q divided by r. Well, in this case, the distance is just the distance d, so this is going to be equal to k q divided by d. Okay? And that's it. Now, we want to compare this in a way to this other case, because I'm really kind of asking the same question twice here. You'll remember I asked a question very similar to this last time, or not last time, a few classes ago, where we had this distance d here, but we wanted to find the electric field, right? So between these two, what's the big difference? Well, there's kind of two differences between these calculations. What's the difference between the electric potential and the electric field if I wanted to find it at this point?
R squared.
R squared's one. Yeah. Did you have another one?
Q.
One more time?
The sine of Q.
Sine of Q, that doesn't really change between these, but there is one more important thing. So the R is one, yeah.
It has a direction.
Yeah, it has a direction, right? So if I want to find the electric field, I have some direction associated with it. But the electric potential doesn't care about the direction. The electric potential only cares about what the distance is. So this is what we call a scalar quantity. So scalar quantities are just like numbers. These are things that we're actually really used to, right? Basically everything we did before we did physics was just a scalar quantity. We didn't care about the direction it pointed. Whereas vectors, we care about the direction. So you can see like the advantages of, even though this is a little bit more abstract, it's easier to work with the electric potential in some cases than the electric field, because the electric potential is a scalar. This is a vector. And we do care about the direction of the vectors. Now, there's another question that follows up on this, and again, this was built very much out of our discussion of when we did this for electric fields. We want to do the same thing here, where now I want to find the electric potential not along the x-axis, but up at some angle like this. But we're still finding it at the distance d. Okay? And we won't, we can discuss it now. We don't have to spend time independently here. What is this electric potential? Go ahead. It's the same, right? Why is it the same? Because the distance is the same, exactly. So if I have this case now, where I have the plus q, and this is some distance d, where these are still the same distance, again, the electric potential doesn't care that I'm up at an angle or I'm just along the x-axis. It only cares that that I'm this distance d away. And this leads into the other question that I asked here, and that's draw the lines of equal potential. Well, the lines of equal potential for the point charge are just going to be the set of all points that is equidistant from here, right? And we know in a plane, that's just going to trace out a circle. So everywhere on this circle has an electric potential with value, this is going to be kq over d. If I wanted to find this at some distance 2d, then we'd have another circle. I can't draw the whole thing here, but we can imagine the circle goes around here. This is V at 2D is equal to KQ over 2D. Okay? Now, the other question that's embedded in here is, well, what's the difference between these if this is positive or negative? So what's going to change with this equation when I evaluate this with a positive charge or a negative charge? The sign of the electric potential changes, right? Because if I plug in a plus Q here, this is plus. Plug minus Q, it's minus, okay? One last thing, I don't know if my next slide leads into this, it doesn't, so we'll talk about it now, is to think about what the relationship between the electric field and the electric potential is. And so, if I'm looking at, let's say this is a positive charge. Let's say this is a positive charge. So if this is a positive charge, then this electric potential, this is going to be the KQ over D, and this one is going to be the KQ over 2D. Which one of these is larger? KQ over D, right? Because this is like the difference between 1 and a half, right? A half is smaller than 1. So this one's bigger than this one. How's the electric field going to point if this is going to be a positive charge? It's going to radiate away from that charge, right? So our electric field is going to point like this, okay? Now, there are two things that we can notice here. One is the relative orientation between the electric field and the electric potential contours, or the equipotential contours. So how's this line and this line, how are they oriented relative to each other? They're perpendicular to each other, right? So one thing we know is that electric field lines are going to be perpendicular to equipotential contours. What's something else we know? This has to do with more the direction that these are pointing. And how successive equipotential contours are related.
Yeah. Electric field points in the direction of D.
Exactly. So remember, this is like saying this is 1. And this is like saying this is a half. So not only are the electric field lines perpendicular to the equipotential lines, but they point from the higher electric potential to the lower electric potential. And what we see if we kind of reversed our scenario here and we said, okay, well, what if I had the negative charge? So if I have the negative charge here, our equipotential contours kind of look the same, right? There's still going to be rings here. But now this is going to be minus KQ over D. This is minus KQ over 2D. So we know our electric field lines are going to point perpendicular like this. And if we remembered the way that we drew electric field lines before, we knew that it was going to point towards the center. But does this obey the same rule? Well, this is like negative a half. This is minus 1. Negative a half is larger than minus 1. And so this points from the larger to the smaller. Okay, so it obeys the same rule even if this is a negative charge. Okay, so we're going to get a little bit more practice with this in a second, but for now, what we'd like to do is to do a little bit of dimensional analysis to figure out what the unit of electric potential is. Remembering, actually, I give you what you need up here already. Okay, so this is another one of these dimensional analysis problems. Go ahead and take a couple minutes to look at that one. Okay, so let's go ahead and talk about this one and proof why I shouldn't try to do these in my head. So let's start from our table to show how this is true, right? Well, we know what the units of force are, right? What are the units of force? Newtons, right? So this is a Newton. So to get to potential energy, what do we say this has a unit of? What's the unit of potential energy, or energy in general? So somebody said it. Joules, right? So this has units of joules. How do I go between these two? Well, if I look at this equation, what's the difference between them? This one doesn't have a charge, right? So what I can say is that the potential energy, U, is going to be equal to Q times V, right? And so V V is going to be U divided by Q. And so if we want to find the units of this are the units of U over Q, which is a joule per Coulomb. But a joule, we know, is a Newton times a meter. And a Newton is a kilogram meter per second squared. And so if we work backwards all the way through this, what we end up seeing is that this is going to be a kilogram meter squared per Coulomb second squared. Okay? Any problems with that? This is kind of usual tricks that we play with dimensional analysis. Okay. Okay, I already kind of explained this one, so I want you guys to do it now yourself. But consider a charge that's sitting by itself in empty space. Draw the electric field lines and equipotential lines for this charge, and do the same thing for the negative charge. Okay, and then we're gonna talk about something kind of interesting about this afterwards. All right, so let me go ahead and put back what I had here, and we'll talk about this. And then what we're going to do is we're going to kind of, not literally, because they'd be kind of pissed off at me if I did this, but we're going to not literally, we're going to figuratively rotate the board and see what these look like in 3 dimensions. So if this is my positive charge, we know our electric field lines go like this, and our electric potential contours, or equipotential contours, go around like this. And if we had some V1 and some V2 here, what we'd say is that V1 is greater than V2, right? Because the electric field lines point from high potential to low potential. If we had a negative charge here, then what we would do is we would, again, draw our electric field lines. So here the electric field lines go in, and our electric potential contours. And so again, if we label this V1, V2, in this case, V1 is going to be less than V2, right? Because the electric field lines are pointing from higher potential to lower potential. Now, let's think about what this would look like if we had some z-axis here. And for this z-axis, we were plotting what the values of these were. And so larger V1s would be further along this way. Lower V1s would be lower down this way. And so what we're doing in effect is we're drawing what are called topographic maps. Okay, so this is representing on the right side what the electric potential looks like for the positive charge, and on the left side what the electric potential looks like for the negative charge. And these equipotential lines that we're drawing here are actually akin to something else that you might have seen before. So I call this a contour map. This is not great for this slide. So what this is like a topographic map of a mountain, right? So on the right-hand side here, what I have are equivalent to what the equipotential contours are. On the left-hand side is kind of a rotated view of this mountain, so that you can kind of see that for the values that I have here at the top, it's a little hard to see, but there's 125, 100, 75, 50, 25. The larger values are indicating higher points on the mountain. Okay, so if you study geology, or if you look at literal topographic maps of geography, that's what it's telling you when you see these lines. Okay, and you can see that a little bit better here. So this is representing a mountain, or a series of mountains, where the center of these rings are going to be the highest point of elevation in this case. But they could also be the lowest point of elevation, but the way that you would be able to tell that is by looking at the successive values of these. And so you could say, am I going from higher values to lower values? Oh, okay, that fills it in. So now what we want to do is we want to do a little bit of an activity here using this knowledge that we have of how equipotential lines can look like topographic maps to look at this problem that I have here. So this is just a parallel plate capacitor with some 40 volt electric potential on the positive, minus 40 volt on the negative. And what we want to do is we want to draw lines of equal potential, and we also want to think about what the topographic map is going to look like here and why. And ultimately what we're going to do is we're going to correlate that to the electric field and how a particle would move in the presence of that electric field, or the equivalent way to think about it is if the particle moves from a point of one electric potential to another, what's its change in energy, or what would its tendency be if it was a positive or a negative charge, depending on what the change in electric potential is between 2 points. Okay, so go ahead and talk about this one for a little bit, and then I'll come around and answer your questions. Okay, so this is a little bit difficult conceptually, but it's getting to a really important point when we talk about the electric potential. And so let's first start by figuring out what the electric field lines are, and then applying our rules to understand what the electric potential looks like, and then in turn what the hill is going to look like. So we have these two plates of the capacitor. So this is some plus charge. This is some minus charge. And this is at some voltage of 60 volts, plus 60. This is at some minus 40. So the first thing we want to do to start out here is to draw what the direction of the electric field is. Okay, so how's the electric field going to point here? What do you think?
Right.
It points right? So this points from the positive plate to the negative plate. So why is it going to point from the positive plate to the negative plate? What do you think?
Because it goes big to small.
Right, so one reason is because the electric field points from high electric potential to low electric potential. There's another reason. What's the other reason? What do you think?
The electric field lines from the positive point away, and then the negative.
Right. So if we think about it in terms of charge, electric field lines point from the positive and they point to the negative. Okay. So now what we want to do is we want to draw what our equipotential lines look like. And what was the rule that we kind of established when we were looking at the point charge in terms of the orientation of these? So one rule was they point from high to low, right? There was another rule, and it had to do with how the electric field lines are oriented relative to the equipotential contours. Do you remember what the rule was? They're perpendicular to each other, right? So whatever the electric potential contours are going to look like have to be perpendicular to the electric field lines. And so I told you here that because of the spacing, because I have 60 volts, plus 60 volts and minus 40 volts, there's a particular number that we could put in here. I think it was 4. So the first one is going to be 40 volts, and then 20 volts, then 0 volts, then minus 20 volts. Now, I also it isn't spaced exactly to scale, but imagine that this distance is the same as this distance, is the same as this distance, same as this distance, same as this distance. Okay, so now what we want to do is we want to plot or draw what this hill is going to look like if I wanted to take this and kind of like turn it like this, okay? So in order to plot this, let's start here and walk our way over to here, okay? So this is plotting the electric potential V as a function of X. So this is the V axis, which is what I'm saying is pointing out here, and then the X axis is just along this direction. So what's my first value for V? 60, right? So let's say that starts at 0. How's that going to look on this axis? Is it going to be positive? Is it going to be negative? Is it a large value for the range that I have, or small value? It's a large value, and it's positive. It's the largest value. So we say that this is our 60 volts, right? And we want to go to the next point here, okay? So what's the next one we have? 40 volts. 40 volts, okay? Then 20 volts, and I didn't do this to scale. Let me rescale this. So this should be roughly a third. So this is 40 volts, 20 volts, 0, minus 20, minus 40, okay? So if we connect these together, we have some hill that looks like this, okay? Now, the next question is, and we can see this a couple of different ways, but let's kind of establish a rule for putting charges on our electric potential hills that we have here. So we want to know what's going to happen if I put a positive charge here, right? So in terms of the forces, we kind of know what's going to happen, right? So if I put a positive charge here, how is this going to act? We know something about the direction of the electric field and you know what the plate looks like. Somebody's doing it over here, right? So positive plate, positive charge. This is going to go this way, okay? What does that say that this would kind of tend to do on the hill? It's going to go down the hill, right? So a positive charge is going to go down our hill. What if I put a negative charge here? Well, let's put the negative charge in the middle, okay? So what's going to happen with the negative charge? It's going to go this way, right? Because it's attracted to the positive charge. It's repelled by a negative charge. What does that mean in terms of our hill? This kind of defies gravity, right? It doesn't quite follow the full intuition that we would have. But negative charges go up hills, okay? So this is kind of a way that you can think about what's happening in these cases, but we're also going to do some calculations here, but I think it's instructive to look at this in this kind of conceptual way and say, okay, well, there are two ways that I can think about this. One way is strictly in terms of the force in the electric field. That's where we are here, in a sense. We're not talking about point charges explicitly here, but we are talking about forces in the electric field. But we can also talk about it in terms of the electric potential, and the electric potential is corresponding to these hills that we draw. We're saying I have some large electric potential, some small electric potential. What's the tendency of the positive charge to do? The tendency for the positive charge is going to move from the high potential to the low potential. What's the tendency of the negative charge? It's going to move from the low potential to the high potential. And if we look at this in terms of the hills, then positive charge goes downhill, negative charge goes uphill. Okay. This is a little new, a little abstract, but we're gonna do some more problems. I think it'll make a little bit more sense. Okay. So let's look at this next question. So here I have these equipotential lines here, very similar to the situation that I have here. I put this positive charge here. What's the direction that this positive charge is going to want to go? Okay, so let's go ahead and talk about this one and kind of walk backwards through the arguments that we were making here. Because now what I give you here is I give you the equipotential lines, and I don't give you the hill, I don't give you the electric field, I don't give you the charge. But we want to see again how all of these things are equivalent to each other. So we could start and we can answer this question just by applying a rule to say that the positive charge is going to move from higher potential to lower potential, right? And so what direction would that point then? It's going to point this way, right? It's going to point to the left, right? But we can go a step further here, because what we want to do is we want to, again, draw upon the equivalency of all of these ideas and show how if we have this drawn this way, we can come to some other conclusions as well. So if this is the arrangement I have this 35 volts on the right and this 5 volts on the left, what should the direction of the electric field be? Direction of the electric field should be to the left, right? Because the electric field is going to point from high potential to low potential. So we have a positive charge in the presence of an electric field. What's the direction of the force acting on that charge? It's going to point to the left, right? Because, correct. I'm mixing my rights for when I mean correct, when I mean directions. But, so if I have this electric field, it points this way. I know that in vector form, F is going to be equal to Q times E. If this is a positive charge, the force is the same direction as the direction of the electric field. And this was the same thing that we just said, right? Now there's one more way that we can look at this, and that's in terms of the charge. So if I know that the electric field points this way, what should the arrangement of charge be if this was the electric potential between capacitor plates? What charge do I have on the right side? Positive charge, right? Because if this is an electric field going this way, I need positive charge to produce it. On the left side, that could mean that these are negative, because electric field points from positive to negative. So if we think about it like this, now we don't have our electric field lines, we don't have our electric potential. I put a positive charge here. How's it going to act because of these charges? It's going to move to the left, because positives repel. A positive repels a positive, a negative attracts a positive, and so because of that, it's also going to go to the left. So the last way that we could look at this, and this is to go like the other direction, we have the values of the electric potential for all of these lines. We could draw our hill here. And so if we drew the hill here, what we would see is that on the right side we have the highest values, on the left side we have the lowest values, and so our hill is going to look something like this. Put a positive charge on the hill, it's going to go down the hill. Down the hill is to the left. Okay? So there's really 4 ways that you can look at this, and they ultimately really point back to these equations and how they're related to each other. But it's important to kind of put all of those pieces together in order to understand the full picture. Okay? Let's look at another one. So now we have this case. What we want to do is we want to rank the magnitudes of the electric fields in these 3 regions. Now, I haven't given you an equation for this yet, and you might have seen it in the lab, or you saw it when you watched the video that I gave you. But you want to think about this in terms of differences. The electric field is ultimately related to the differences between the distance and the electric potential. Okay, but go ahead and take a couple of minutes to talk about this one, and then we'll come together and talk about it. Okay, so let's go ahead and talk about this one. So the key to understanding this one is actually to draw the hills that we have that are associated with each one of these. So what I did here was I drew what the equipotential contours look like, and now what we're going to do is we're going to take each one of these and kind of rotate it to look at what the hill is going to look like. And so, guys, can we stay on topic? Thanks. So when we look at these hills, what we can do is we can plot them. So this one is going to start from a value of 5 and go up to 10, but it's the same interval in distance across here, okay? So this is going to give me some line that's going to look like this, okay? So this is just some line that goes up like this, okay? Now, this one looks really similar, but we're starting at a different value, and so I have to shift my axis here. So if I shift my axis down, so I'm trying to move my axis down as far as I can, and it's not going to be exactly to scale, but this one is going to look like this. So this is going to have roughly, I'm trying to draw this to scale the best I can, roughly the same slope, or it's exactly the same slope, right? Because this interval here is the same as this interval here, and the difference in potential between here and here is the same. We can do the same thing for this one, but this one's going to be a little bit different than the other two. So this one, I have the same change in electric potential between these 2 points, but it's much shallower, the angle that I'm going to have here ultimately, because the spacing between these points is larger, okay? So this is more what it looks like. This is more what it looks like, okay? So ultimately, the electric potential is related to the electric field here by saying that the electric field pointing in some x direction is going to be equal to the negative change in electric potential divided by the change in distance, okay? And this corresponds to the negative slope of this line that I have here. And if we look at these, even though these are different altitudes, they have the same slope. So this is kind of like saying, well, if I have some hill on Everest or I have some hill at sea level, it doesn't really matter how high the hill is. It matters what the change in the hill is. The ratio of the change in the x, so in this case, the change in the electric potential. So the fact that the altitude is higher actually doesn't matter. And what's interesting about that is now if we talk about what's going to happen if I put a positive charge, let's say we put the positive charge here, a positive charge here. Even though the values of the electric potential are the same, or sorry, the values are different between here and here, the important thing is that the change from one position to another is not going to be different. And so this one and this one actually behave exactly the same. It's like they're going down a hill with the same slope. So this one, on the other hand, is going to be different. This one, because the hill is not as steep as these ones, is going to be slower than these ones. Okay? Any questions about that? Okay. So yeah, the answer is that 1 is equal to 2, which is greater than 3. Okay. So now we're going to put an electron on the middle equipotential line, so the equipotential line at 0, and let it go. What's going to happen to this electron? Okay, so let's talk about this one. So it is and it isn't a trick question, because you might think that since there's an electric potential of 0 here, I'm putting this electron on the electric potential of 0, it should just stay there maybe, right? Because maybe nothing's happening there. It's the electric potential of 0, but the electron's not caring about what the electric potential is. It cares about the difference in electric potential, or the ratio of the difference in the electric potential to the distance, to the adjacent point of equipotential that we have here. And so in this case, this is, if we drew the hill, again, we can always start with the hill. Well, the hill is just going to look something like this, right? So even though this is 0, I put the electron on it, it's not going to just sit there. So if I put an electron on a hill, what's it want to do? It wants to climb the hill. So this one's going to go to the right. Okay? You have to be careful with the signs. So if it's positive, it goes to the left, negative, it goes to the right. Okay. Okay. So now we are going to do a little bit of a calculation. This is still kind of conceptual. So this one says the charge Q is at a point in space where the electric potential is 5 volts, is released from rest and later is observed moving with a certain speed past another point in space where the electric potential is 10 volts. The charge is going to be positive, negative, or you can't tell. So go ahead and talk about this one. Okay, so let's talk about this one. So what do we think? Is it positive, negative? Do we not now have enough information? We do have enough information. Should be negative, right? So why do we know it's negative? Well, we don't really know left or right or up or down how it's going to move, but I'll choose to make this so that this is plus 5 here and plus 10 here. And so I put whatever my unknown charge is here, it's going to go this way. And so that means if I draw this, what it's doing is it's going up the hill, right? Only negative charges go uphill. Positive charges go downhill, so this should be a negative charge. It's a negative charge. Okay, so let's look at another one. So let's talk about this one, and there is a little bit of intuition here, but to completely get the answer correct, you also have to bring back the equation to get the sign correct on what the work is done by the force due to the electric field. And so what we can do here is we can draw our hills for these to say that for the first one, we're going from some high point to some low point. So this is going to look like this for the first one. For the second one, it's also going to look like that. For the third one, it looks like this, okay? And now we have our charge. And the charge is going to, in these two cases, naturally go down the hill, which is actually the same direction as the electric field, right? Because the electric field here points this way. Electric field points this way. Electric field here points this way, okay? And ultimately, because this is a positive charge, the electric field and the force are pointing the same way. So in order to rank the works on these, we need to, in a sense, not explicitly do the calculation, but we need to be cognizant of the signs that we have here. So if this force is pointing this way and the distance that I'm going is this way, are these parallel or anti-parallel? They're parallel, right? They're the same direction. So what's the angle between this distance and the electric field? 0, right? So cosine of 0 is 1. So this gives me a positive work. So this one is positive, this one's positive, and they're the same. This one, the direction that I'm moving, it's still going to the right, but my electric field is pointing the opposite direction. So are these parallel or anti-parallel? They're anti-parallel, right? So that means that the cosine of the angle that I want is 180 degrees. These are in opposite directions. And so that gives me a negative sign, because cosine of 180 is negative 1. And so this gives me a negative work. But the absolute values of all of these works are going to be the same, right? Because the electric field in a magnitude is the same, it points different directions. And so what we have here really is that the work done by 1 and 2 are equal, and those are going to be greater than the work done by 3. Okay, so the intuition doesn't completely save you, but it does help you kind of draw the picture of how this looks. Okay, I think we have time for one more. So we'll start this one. This one's actually a calculation, but we'll pick up with this one next time. Or actually, what time is it? It's 47? Okay, let's just go. Okay, that's going to be it for today. We're going to pick up with this one next time. How many more of these do I have? Okay, actually not a lot. Not a lot.